So there are two parts to this question. The first part is just an open response really. They're trying to get you to apply some physics that you know to a novel context. And actually this is really about how models change over time to fit evidence. It's not really about the ultraviolet catastrophe at all. This question is actually just drawing out some knowledge and understanding from quantum. So basically you have to recognize where that knowledge and understanding goes, and then it's asking you to do an analysis of some graphs. And that's all it's asking you. Then there's a quantum calculation that you need to be quite slick at doing. You need to be quite practiced at applying the photoelectric equation. But you can do it once you've done a few of those. It really starts to make sense. So the diagram shows radiation curve for a black body radiator. The diagram was obtained from experimental data. So this is how they actually are in real life, if you like. Increasing frequency, intensity. There's a kind of peak. There's kind of peak wavelength. And this is Wien's law, basically. Allows you to calculate that peak wavelength using that constant. In the 19th century, scientists struggled to explain this experimental curve. Okay, one model uses classical physics and produced curve A. So this is this point here. And there's an issue here because you don't see this. Okay, we call this the ultraviolet catastrophe. Here it is here. There's a certain point where suddenly what you expect to happen doesn't happen. The energy still increases, but the frequency doesn't increase for these black body radiators. So what's going on here? Now, a second model quantized the experiment essentially. So it included the idea of energy quantization, the mechanism of the energy emission, and produced curve B. What is the energy emission for this radiator? Well, the energy emission is the emission of photons, which is your first clue. After the clue of quantization wasn't enough to give you some ideas about the answers for these ones here. Both curve A and curve B are shown below the experimental curve for comparison. So the experimental curve's there, B is the first model, A is your second model, B is the quantized model, and A is the classical model. So here's where you need to be really resilient, because you're going to read all that and you think, okay, that's not very familiar to me necessarily, but the clues have given you a clue to pick up marks on these A-star questions. So explain how energy quantization applies to the emission of radiation energy from a black body radiator. So here we're talking about photons. Essentially, this question may as well say, explain how photons are emitted from a thing. Okay, you don't need to worry too much. You just might as well say, explain emission of photons. Quantization refers to the emission of electromagnetic radiation in discrete or fixed, you could say, packets of radiation. And I'm just going to put in brackets photons, because these are the key words they like to see: discrete and photons. Okay, well, what is a photon? A photon is something whose energy is proportional to its frequency. So photon energy is proportional to its frequency. In other words, E equals HF. So they want to see that, but they want you to discuss what it means. Okay? So, that is a hard context. The whole idea of changing models, quantization fitting evidence better than classical physics. But really you need to basically explain to me what quantum physics is all about. Assess the extent to which each model is successful and explain the experimental curve. It doesn't ask you to explain why the data looks like this. It doesn't ask you to get into the quantum mechanics. It asks you to Assess the extent to which each model is successful at explaining the curve. So let's look at how the models explain the curve. Well, this is my experimental curve, and there's kind of two spheres. There's this sphere and this sphere. There's two parts. So my answer, I'm going to talk about part one. How is A or B good at explaining that? And then I'm going to talk about part two. So, part one. Don't need to explain what it's showing. I don't need to explain why it is that as the intensity increases, the wavelength increases up to a point. What I need to explain is how good is A? Well, A is not really good at that point at all. How good is B? So, A is not good. Let's use their terms. I don't like to see the word good. It's not successful at explaining sphere 1 as the model does not follow the experimental curve. What about B? Yeah, B is pretty good for those short wavelengths. It's actually pretty much spot on, isn't it? So B is successful at explaining P. Okay, now part two. So Model A is pretty good on this side. It's not quite as good as Model B, but Model B doesn't quite fit the curve either. You're getting higher intensities through these wavelengths than the actual experiment. So Model A is reasonably successful at explaining sphere 2, sorry. But it's much higher intensities around 1,500 nanometers. Model B, however, is more successful yet intensities are still higher than the experimental data. So I hope that makes sense to you. This question looks like a real difficult one. And I've had students who give me lovely explanations of the ultraviolet catastrophe and why this happens. It didn't ask you for that. It just asks you to look at how the model fits the experiment and give me 4 points. Essentially, compare Model A to this part, compare Model B to this part, compare Model A to this part, compare Model B to this part. Keep it simple. Do what the question asks you. Right, so the idea of energy quantization was used to explain the photoelectric effect. So, the explanation of photoelectric effect was Einstein's photoelectric equation. So let's go ahead and get that. Let's get it ready. HF is phi plus half mv squared max. I'll just leave that. So where this is the energy of the photon, this is the work function to get to the surface of the metal, and this is the kinetic energy that's released. And this is what we're asked to actually work out. So straight away we're ready to go. Ultraviolet radiation is shone into a metal surface. Electrons may be released. So these are photoelectrons. So these are all just clues to get this equation. A cadmium source illuminate with light of wavelength this, so this is lambda. Yes, we're in the right units, that's fine. There's no lambda in this, is there? But we do know, don't we, that for waves, their wave speed is f lambda. So, and the speed of electromagnetic radiation is c. So just write that equation down there. And I can use this to sub in there. If I rearrange for f, c over lambda. So essentially hc over lambda equals phi plus half mv squared. So this is my work function here. My first thing I need to remember is that is a non-SI unit. That is a very small unit equivalent to the charge on an electron times 1 volt. It's the kinetic energy an electron would have if we accelerated it through a 1 volt field. So I need to convert that to joules. So what I do is I follow the unit like it's a formula. So I just do 4.07 times 1.6 times 10 to the minus 19, which is the charge on one electron. And you don't need to remember it. It's in your formula sheet, but once you've practiced a bunch of quantum questions, you're not going to forget that. And also times 1 volt, but let's just times it all by 1. Yep, that's done. Okay, so work that out in joules. 6.512 times 10 to the minus 19. Just keep all the sig figs for now. Okay, so now I can plug this into here. I want to work out the maximum kinetic energy, so I'm actually going to do hc over lambda minus phi, which is this number, equals half mv squared, and I don't need to do anything. That is my maximum kinetic energy that I want. So now numbers in, 6.63 times 10 to the minus 34 is Planck's constant. Again, you are given it, but once you've done a fair bit of practice, you're probably going to remember it. Times c, again, given that. 3 times 10 to the 8, and the 3.0, because the 3 sig figs is 3. Over the wavelength, take away this, now reach for the calculator, and again it's worth writing out the sum you're going to do so that the examiner can follow what you do, in case at this stage, and easily done, you're going to make a mistake. Boom. So the maximum kinetic energy 1.32 times 10 to the minus 19. Is that sensible? Is that a sensible answer? Yes, it is, because we're talking about one electron, which has a charge of 1.6 times 10 to the minus 19. It's in the right order of magnitude for joules. I don't need to convert back to electron volts. I could, but I don't. That seems to me to be a sensible number of electron volts. Here's a good example for answering the question in front of you, not going off on one and getting excited about some physics. They've given you the interesting context, but actually that interesting context is not on our syllabus. It's not on this one. So really they're not asking you about that. They're asking you to do some analysis of this graph. It's also important here to know that just practicing exam questions is not going to get you the deep understanding. Quantum mechanics is hard to understand. The whole electromagnetic equation, that's a difficult topic. It is the difficult topic in first year physics. So you need to go back. If you're struggling to understand that bit, you need to go back and actually go over that topic, watch some videos, read some of the textbook until you really fully understand what's going on there. Remember, with quantum, refer to one photon interacting with one electron.